I'm going to be talking about the conservation of energy, which states that energy can neither be created nor destroyed, only converted from one form to another. First of all, energy, the definition of energy is the ability to do work. And we're going to be focusing on spring potential energy, gravitational potential energy, kinetic rotational energy, and kinetic translational energy. These aren't all the energies, but they're some of the more prevalent things seen in physics. So the difference between potential and kinetic energy is that potential energy reflects the energy caused by an object's position at a given time, whereas kinetic energy reflects the energy due to an object's motion. So for spring potential energy, we can consider the case where you exert a force to make a block compress a spring. And once you release that force, you can expect the block to bounce back out, which gives it the ability to do work and therefore potential energy. Gravitational potential energy is seen whenever you have an object that's raised above a surface. It has the ability to do work as well because, as you can imagine, once it's released, it will accelerate due to the force of gravity and speed up. So this is an example of kinetic translational energy, which is basically the energy caused by a linear motion. And this is its corresponding energy for rotation, kinetic rotational energy. One thing that's also important is that when we consider conservation of energy, it has to be in an isolated system. There can't be any external forces acting upon it. And also we have to remember that we're talking about the total energy of the system. So one might ask, for a block sliding across a rough surface with friction, with an initial velocity that gives it kinetic translational energy, where does that energy go once friction makes it slow down? So this is like, in this case, you can't just consider the block, but you also have to consider this surface. So once it slows down, that's due to work caused by friction. And that energy actually turns into thermal energy for its contacting surface. So the entire system has to be considered when you're talking about conservation of energy. So this is another example similar to the one we were just talking about. So instead of the block having an initial kinetic energy, translational energy, this block is compressed into a spring and thus has an initial spring potential energy. As we would expect with a conservation of energy, the greater x, the greater distance you compress into the spring at the start, the greater spring potential energy, and which would cause a greater kinetic translational energy when you release, when you stop applying that force into the spring on the block. The block will have a greater initial kinetic translational energy, which would then cause it to move a further distance. So that's reflected by our experimental data. As you can see, with a greater x, there comes a greater d.